Hello everyone, let's analyze. So often functions are defined piecewise with different rules for different partitions of the domain. Imagine, for example, modeling a situation where a switch is flipped, a circuit is completed, a discontinuity in the material that you're modeling is encountered. Right? You might have a function that's defined piecewise. So consider, for example, the function that maps the reals to the reals, f of x equals 1 if x is negative, and cosine of x if x is not negative. So given the different rules for how the function is defined on different parts of the domain, if I wanted to analyze the limit of the function as x approaches 0, right? For example, the point at which our definition changes, it's sometimes useful to analyze limits differently on the left and right of the particular points. So we're going to define what it means to have a left limit and a right limit, and how we can use each of those to determine whether the actual limit exists. So let f map a domain D to R. D is, of course, a subset of the real line and has an accumulation point at x naught. Then f has a right limit as x approaches x naught from above or from the right. If and only if, for every epsilon, there exists a delta for which the following is true. If x is in the domain and x is in the open interval x naught to x naught plus delta. Now, let's just stop and make sure that we understand what this means. This means that the absolute value of x minus x naught is less than delta, and that x is strictly greater than x naught. Then f of x minus L is less than epsilon. And this notion is expressed the limit as x approaches c positive. This means x greater than c. F of x is equal to L. So if we notice, this definition of a limit is exactly the same definition as a regular limit, with the exception that x is strictly greater than x naught. Right? Strictly greater than x naught. That is the only difference. We can also define a left limit or a lower limit in the exact same way. The definition is word for word the same, except that x is in the open interval x naught minus delta, comma x naught. And the difference of f of x minus L is less than epsilon. And this notion is expressed as the limit as x approaches c from the left, or c negative, of f of x. Okay. Now, if a function has a left limit and a right limit, and those limits agree, then the function has a limit at that point. And of course, if the function has a limit at that point, then the left limit and the right limit necessarily agree. In other words, it's an if and only if statement written here in this theorem. And in fact, you'll prove that it's true, well, because it's in your homework. So we now address the algebra of limits for functions. In other words, if I am considering the sum, product, or quotient of functions that have a limit at a particular point, can we evaluate the limit of this sum, product, quotient? Now, notice we've actually already have a set of notes that addresses exactly this for functions of natural numbers. Functions of natural numbers, if you remember, are called sequences. Here we're going to address it to more general functions. But you may also notice that the proofs for many of these will be very similar to the proofs we applied to the arithmetic of sequence limits. So here we have the three results all as one theorem. Suppose f and g map A to R and C is an accumulation point of A, and that f and g both have limits at C. Then the function f plus g has a limit at C. Furthermore, the limit as x approaches C of f plus g is the limit of f plus the limit of g as x approaches C. In other words, the limit can be distributed. By the way, this notation here, okay, this just means f of x plus g of x. Okay, f of x plus g of x maps x to a number, so it's essentially a new function that we call f plus g. But just so that we're clear, it really is just f of x plus g of x. Similarly, fg of x is the function f of x times g of x, right? So just so that we honor the fact that f of x times g of x is in itself a function, we call it fg. Okay. Similarly, f divided by g of x is the function f of x divided by g of x, which is defined so long as g of x is not 0. Okay, so if f and g have limits at C, then f times g has a limit at C, and it's specifically the product of the limit of f times the limit of g at C. Right, so all these rules work exactly as you thought they would, and probably as you have used in the past when you took Calculus 1, though without the benefit of rigorous proofs behind each result. Here, for result 3, we need the extra condition that g of x is not 0 for all x in the domain. In other words, f divided by g is a well-defined function. We also need that the limit of g of x is not 0. Otherwise, this term would not be defined. So the limit of the function f divided by g is just the limit of f divided by the limit of g as x approaches C. Now we're actually going to prove 1 and 3, and result 2 is proven in the book. So I would encourage you to read that portion of the book in the assigned reading and pay special attention to it. But also note that essentially we can almost copy, if not word for word, concept for concept, the proof we gave for the arithmetic of sequence limits. So let's look at result 1. So before we get into the formal proof, I would strongly encourage you to pause, go find the notes or the video on the limit of the sum of sequences, and make sure that you read that again and understand it. You'll likely notice that proof is very similar to this proof. And before we get into the formal proof, let's just kind of go over how we're going to use the triangle inequality. So the function f plus g of x minus the sum of the limits, L1 is the limit of f and L2 is the limit of g. Right? That's equal to f of x minus L1 plus g of x minus L2. All I did is rearrange the chairs on the Titanic here. And at this point, since I know that L1 is a limit of f and L2 is a limit of g, I know that L1 and f can be made to be arbitrarily close, and L2 and g can be made to be arbitrarily close. Right, therefore, I'm going to split this using the triangle inequality and say that this is less than the difference f minus L1 plus the difference g minus L2. And I know this term can be made as small as possible. This term can be made as small as possible. And our goal is to guarantee that this term is as small as possible. So, of course, if I want this term to be less than epsilon, well, I need this to be less than half of epsilon and this as well. And that's the idea behind the proof. So let's now rigorously go through these steps. Okay. So we make the assumption and the hypothesis of the theorem. F and G map A to R. C is an accumulation point of A. F and G both have limits at C. As I stated just before, L1 is the limit of F. L2 is the limit of G. Let epsilon be positive. Again, arbitrary epsilon, positive epsilon. So we need to show there exists a delta so that if this is true, then, and this is true, then this must be true. Okay. Now, again, as before, I can make F minus L1 as small as possible. So I can make it less than epsilon over 2. And there exists a delta 1, right, that would guarantee that results, right? Because that's the definition of a limit existing, right? There is some delta 1 that guarantees the epsilon over 2 results. Similarly, there's another delta 2, right? There's another delta 2, that guarantees the G minus L2 result. So if this is true and this is true, then I get that this must be true and this must be true. So in order to make sure that both delta 1 and delta 2 conditions are satisfied, we just choose the smaller of the two. So you say let delta be whichever is smaller, delta 1 or delta 2. Then this being true implies that x minus c is less than delta 1 and less than delta 2. Suppose x is also in A. Then since the delta 1 condition is satisfied, the delta 2 condition is satisfied. We know how to break this up using the triangle inequality to get to this point. We know that the epsilon over 2 condition is met for both differences, and we get that the difference is less than epsilon. Therefore, the limit of f plus g exists and is equal to L1 plus L2. Now, to prove result 3, we're going to use a theorem that we proved last time, specifically a theorem that connected sequences and functions limits, right? There is a if and only if theorem that connected convergence of sequences and convergence of functions. Of course, the theorem is in your previous notes, but just to have the theorem handy, it's stated below, though this time using standard mathematical shorthand. Okay. So the limit of f as a, the limit of a function that maps a to r at c exists and equals L if, right, if and only if for all sequences in the domain with no entry equal to c, and the limit of that sequence being c implies that the limit of f of xn is equal to L. So we're essentially going to use this theorem and apply it to the function f divided by g. Well, because we know that f has a limit and g has a limit. And so the fact that f and g has a limit implies that this statement is true for both f and g. In other words, I can turn this numerator and denominator into sequences. And, well, we already have results for the quotient of sequence limits. So suppose xn is an arbitrary sequence converging to c, never equal to c, right? Then, right, f divided by g of xn is itself a sequence, and it converges to L1 over L2, right? Again, that follows directly from the result on the quotient of sequence limits, right, from our previous notes. So since this result implies this result, we've shown for the quotient this bottom condition is satisfied. And because this bottom condition is satisfied, it implies the top condition is satisfied for the quotient. Right? Therefore, f divided by g has a limit at c and is equal to L1 divided by L2. Okay, and that's essentially the proof. Now, for result 2, we omit it here, but again, confident that you can read the proof in the book with understanding. And of course, you could also, just like for the quotient result, transform that into a sequence product using the theorem that connects functions and sequences and get the proof that way. That's all for today.